Okay, so let's chit chat about these problems. So, when you have gravity, so on all of these problems, we're going to define down as being a negative value. So this is what we talked about yesterday. You either drop it or you throw it up in the air. So if you look like on this first problem, number 5, right? So you're on top of a bridge and this thing is going to fall a certain distance. So at the beginning, do not make this complicated. All I'm asking you to do is draw some velocity vectors. Oh, okay. Here's V1. So once you draw V1, when you draw V2, there's only 2 options. Either V2 is bigger than V1, or V2 is smaller than V1. That's it, okay? Those are your only options. As the ball falls, what's going to happen to the velocity? Bigger or smaller? Bigger. So draw V2 a little bit bigger. Now, if your velocity vectors are getting bigger, which direction is your acceleration vector going to point? Same direction, opposite direction? Same. So we're defining down as being negative, so those are going to be some negative velocities, and that's going to be some negative acceleration. That's it. That's all you have to do. Not make this complicated. Now, you're going to calculate the velocity after each interval of time. 1 second, 2 seconds, 3 seconds, 4 seconds. Okay? So gravity is like the quintessential example of uniform acceleration because it's a constant force. And we're always assuming that we're in a vacuum. Obviously, if we're not in a vacuum, that doesn't hold. But don't worry about that for now, because then you have to worry about drag coefficients and terminal velocities, and it gets real ugly real fast. So, and again, you have to understand what acceleration is. It's the rate at which your velocity changes. So if you start at 0, okay, 1 second later, you're going to be going negative 9.8 meters per second. That's what the number means, right? After another second, you're going to add another negative 9.8 to it, and another negative 9.8, and another negative 9.8. So each second that falls, your velocity changes a fixed amount, okay? Again, that's not how fast you're going. So this is why hopefully your velocity time graph looks something like this, okay? Should be a nice, perfectly linear function, and the slope of that line, wait for it, should be negative 9.8 meters per second squared. And let's say you go say, oh, Mr. Burkamp, how do I know that? The reason that you know that is because of this equation. This is V equals V naught plus AT. So velocity changes as a linear function of time because it's just acceleration multiplied by time. Okay? So that's why it changes the same amount. It's a slope intercept. It's algebra. Okay? We just call it physics because we're cool like that. But at the end of the day, it's a linear function. Okay? Now, the distance is a little bit more complicated. Okay? It's a little bit more complicated because of the fact that it's not, the position isn't changing the same in each interval. And I know the position isn't changing the same in each interval because it's 1/2 AT squared plus V naught time. Okay? So this, we dropped it, the initial velocity is 0. So as soon as I see t squared, I know, oh, this thing is not a linear function because it's t squared. So you got negative 9.8. You're just going to plug in times. 1 second, 2 seconds, 3 seconds, 4 seconds. And what you should see is that what this number is generating is how far it's fallen at the end of each interval, assuming that you start at 0. Okay, so if you start at 0 at the end of 1 second, you should get like negative 4.9 meters. At the end of 2 seconds, obviously that's going to fall farther in the 3. So hopefully your position time graph looks something like this. Okay? Now, again, understand how your velocity time graph matches up with your position time graph. So if you were to come out here at 1 second on your, and this is on your position time graph, at that 1 second mark, and you were to draw a tangent line, that would have a slope of negative 9.8 meters per second, because that's how fast it's going at the end of 1 second. If you came out here to 2 seconds, that would have a slope of negative 19.6. 3 seconds, that's how it's going to progress. So your position time graph is curved because of 2 reasons. Mathematically, it's curved because you're multiplying it by time squared. Okay? It's a quadratic function. That's the reason number 1. The other side of it is that the reason that it has to be a quadratic function is that your velocity is getting faster, so your slopes have to be getting steeper. Okay? So hopefully that's what those 2 lines look like. Okay? Cool with that. On question number 8, with the kangaroo, by the way, if you're ever driving it, and kangaroos are nocturnal animals, so just if you ever drive the outback of Australia, just watch out for kangaroos. Okay, they will completely mess. It's like hitting a deer in Kansas. Okay, hit a kangaroo, it's just going to mess up your car. And it's funny in Kansas, if you live out in the country, you have like what they call like bull guards or cattle guards on the front of your truck. Okay, in Australia you have blue guards on the front of your vehicle, so in case you hit a kangaroo, it doesn't mess up the front of your car. So, little known fact if you're ever driving in the outback of Australia. So, here's what's happening on number 8. So, when you throw something up in the air, here's the main idea. Topher Kinism, when it's at the top, what's its velocity? 0. Why? Relative mass, and your velocity is 0 because you're changing direction, right? Okay. So, if you look at what's happening on number 8, with what velocity did it leave the ground? Okay? Now, here's the deal. Notice on this one, on number 8, what variable did I not give you? Time. So it's the only one that doesn't involve time. That equation, right? So right away, on number 8, you're going to go, oh, here is Conga the kangaroo, okay? Right? Okay? Kanga the kangaroo. Kanga's going to jump up in the air, right? With some initial velocity that I don't know. But when the kangaroo gets to its maximum height, the final velocity is going to be 0, okay? So it's going to go from some velocity to 0, and the kangaroo jumps up to a height of 1.5 meters, which is about like EA, okay? Pretty decent jump, okay? So 1.5 meters. So go to that equation. You have v squared equals v naught squared plus 2ad. You know your initial velocity is your unknown value. That's the one that you don't know. Now, this is where you have to solve these variables first, okay? So you're going to sit here and go, okay, I need to get v naught by itself. So that's going to be v squared minus 2ad. Square root of that is going to equal v naught. So this is where you have to pay attention mathematically about what's going to happen. So you're going to have 0 squared minus 2 times negative 9.8 meters per second squared times 1.5 meters. Okay, so this is where the magic happens. So I've got 0 minus a negative number. Now I have a positive number underneath the radical. Okay, so this 1.5 is a positive displacement because the kangaroo is jumping up in the air. So I have 0 minus a negative. If you do these right, you shouldn't end up with negatives underneath the radical. And if you have negatives underneath the radical, just don't ignore them and go, oh, just act like they're not there, okay? These aren't freshmen that you can just ignore and there's no ramifications. If you have negatives underneath the radical, you have done something fundamentally wrong, okay? Either your displacement has the wrong sign, something has gone south, okay? So that velocity on 8b should be around, This is ish around 5 to 6 meters per second. Okay? On number 9, with the finding the height of the bridge, which is actually a very valid way to do this, that height should be in the mid-30s. Okay? Your answer to that first answer to number 10, that maximum height should be around 30 meters. And let me see. Now, let's talk about 12. So on number 12, 12 is almost identical to the kangaroo problem, other than the fact that we're throwing the ball up in the air. So your answer to 12A, listen to me very carefully. Your answer to 12A should be something close to the legal drinking age. Okay? Not what you think of it, not what you think it is when mom and dad are out of town and you're there with your big sister. Okay? It's what the legal drinking age is. Okay? And if you're not sure, ask me after the class. Okay. So, here's the idea. Is that you're on Earth and you're going to throw this thing up in the air, and it's going to go to a height of 25 meters, which is a decent toss. This ceiling is like 25 meters, okay, or 2.5. So 25 would be 2.5. It's about, if it's 10 times higher, it would be like 25 meters. Okay, so that would be a pretty decent toss to get that thing to go that high. Okay? So now imagine this. And here's what when you have problems like this, you have to focus on what you're holding constant and what you're changing. So now we're going to go to the moon. And we're going to throw it with that exact same velocity. A little bit. It's like, what is that noise? So I'm going to throw it with that exact same velocity on the moon. Now, don't get so wrapped up in these equations, okay? Just ask yourself, if I throw that ball with the same velocity on the moon, is it going to go higher or not as high as I do on the Earth? It's going to go higher. Okay, so you know your answer has to be bigger than 25 meters. Okay, just think it through. Like, oh yeah, it's going to be a bigger number. If you get a height less than 25, you've done something wrong. Okay, on number 14 with the pyrotechnic one, that height should be between 100 and 150 meters. And the only way you can do that one, this is why I said don't use that equation. The only way you can do 14A, and this is the only way that you can do 14A, is if you do 1/2 AT squared plus V naught time. That is the only way you can do that problem. That's it. There's no other way. You have your time, you have your acceleration, and here's what's critical. That has to be negative 9.8 meters per second squared, okay? If you make that positive, then you're adding two positive values together and you're going to get an answer that's way too big, okay? So this thing is shot up, has an initial positive velocity. You have to use negative 9.8. That's the only way you can do that problem, okay? Now, let's talk about number 15. So here's the situation. You've got 3 young lads standing on top of the bridge. You've got Bubba, and you've got Larry, and you've got Daryl. Okay? Now, let's start with Larry. Okay? So Larry's the most chilled of all of them. Larry's just like, okay? So he's just standing there. He happens to have, I don't know, let's say a bowling ball, okay? So he's got a bowling ball. I don't know why, but he does. So he's got a bowling ball. And he goes, you know, I'm just going to drop the bowling ball. So Larry's just going to drop the bowling ball, right? Okay? So what's the initial velocity of the bowling ball? 0. Okay? So on that one, here's your velocity time graph. So what's Larry's velocity time graph going to look like?
Negative 9.8 meters.
Starting where?
At 0, 0.
0. and it's going to slope down like this at
-9.8.
meters per second squared, right?
Yeah.
Okay? Velocity time, there's 0. Because he's just going to drop this thing, right? Okay. Now, Bubba, on the other hand, Bubba goes, oh, man, I want to throw mine up in the air. So Bubba's going to do this, okay? So what's the difference?
Just start higher.
So we're going to start higher on what?
The velocity time.
Velocity time graph, because he's going to start with some positive velocity, right? So this is going to be Bubba's, right? Now, we'll talk about this more. This is this concept of Jedi Stofewalk, which means stop the force and watch. So as soon as he throws that ball up in the air, what's the only force acting on it? Gravity. What's the acceleration caused by gravity on Earth?
Negative
9.8 meters per second squared. So is it going up in the air? Yes. Is gravity still the only force acting on it? Yes. So what's Bubba's line going to do? Like this? Parallel with Larry's?
Yeah.
Yes.
Yes. Why?
Because they have the same slope.
They have the same slope. They have the same acceleration. Okay? So the two lines are going to be parallel. Good with that one. Now, I'm not going to do this one. But Daryl has anger issues. Okay? So, I had a golf ball at some point. I'll use this. So, Daryl has anger issues. Okay? Always has. Never been a happy lad. And so Daryl's up there and he goes, oh, screw it. And he's going to throw his down. Okay? Now, when Daryl throws it down, as soon as it leaves his hand, what's the only force acting on the ball? Gravity. What's that acceleration going to be? Negative 9.8 meters per second squared. Right? Okay? Because everybody says the misconception is that when he throws it down, his acceleration is actually going to be faster than if you throw it up in the air because he's throwing it down. Okay? And it is while it's in his hand. But as soon as it leaves his hand, doesn't matter. It's only going to have gravity affecting that velocity. So it's just going to be, here's Daryl. Daryl has anger issues. So all three lines are going to have the exact same slope. Okay? The only difference is the starting velocity. Yes?
I have a question. It may be stupid, but does our...
You know, that would be the first time I've ever had a stupid question asked of Mike in almost 30 years of teaching.
I don't know. I mean, this one's pretty stupid. Does the x-axis have to be on 0, or can it be at negative 30? Like if I set my x-axis at negative...
What?
This is the stupidest question anybody's ever asked you.
I also have a stupid
Why are you
question,
making this
but
difficult? Look,
Well, I may or may not
Look.
draw my x-axis at negative 30.
Just a reason.
what? You have to start at 0 because Bubba starts at 0.
I'll change it. My bad, boot camp.
is there a certain way you read vectors like left to right, like when you're reading something? Because Ella told me my vector, like, why does it get...
Oh my god.
Like which one? Okay, this is too vague. Give me some concrete.
So on AA, you know, going up, the vector goes from bigger to smaller?
Yeah, so
Yeah.
so with the
Yeah.
kangaroo, right?
Yeah, I did that right,
So
though.
on the way
but-
up, okay, so here's kangaroo's V1, right?
Oh, I didn't do it like that.
How did you do it?
I did it from the side.
Which
I did
direction
it
is
from
the
the side,
kangaroo
too.
jumping?
Am I not
Oh,
supposed
wait, you
to
can't
do it from the side?
Which direction is the
Oh,
kangaroo
crap.
jumping?
Okay.
I know it's up.
What-
No. Everyone
Oh, no.
Yes, because otherwise it looks like he's jumping sideways.
Good to know.
Good thing you asked that question.
Yeah. But that also isn't...
Wait, so there's two?
Maybe 5 feet down there.
Because I figured if I was jumping,
Wyatt, shut up.
I mean, if you're jumping,
I agree, sir.
I hate Wyatt.
You're literally...
Okay, hate is a strong word.
I dislike Wyatt.
I can give you that. But he's got brownies.
this is great concept.
That's about it.
Oh, you're putting that in your story. Alright, I fixed it.
If I had something, let's not talk about it.
Yeah, you could get brownie points. Ha ha ha.
Yeah, literally. Yeah.
Alright,
Okay.
I'm good now.
Anyway,
Wait, 5 also
so
goes down.
your answer to 4A
It does?
should be a really, really, really small acceleration because that you're stopping a really, really, really big supertanker. And then your distance is going to be really big, okay? So your answer to 4A should be something times 10 to the negative third, and your answer to 4B should be something times 10 to the positive third. And pay attention to significant digits, okay? Pay attention to significant digits. If you have an acceleration of, say, let's say you write down an acceleration hypothetically of negative 0.007, let's just say. Let's just say. How many significant digits does that have?
One.
One.
Oh no.
The zeros are freshmen, they don't count, okay? After you get past
No,
the...
like, no.
Now, if you had 0.070, then you would have two significant digits, okay?
Where?
So, if you have that, that only has one significant digit.
No, I just need to go.
Okay.
Oh.
Oh.
Anything else on this assignment
Oh.
at all?
Are there any more vectors?
Yeah, on 5. Change 5.
Okay, I did that.
Going
What
once,
does it look
going
like?
twice,
Looks like this?
Taylor Allen.
Okay.
Huh? Number 10?
Songs.
Okay. So on number 10, here's the deal.
That's not 8.
Taylor, what's the initial velocity of the ball? Okay, so there's your V naught, right? Why would this stupid thing right?
Not the series though.
I'm the main antagonist in this story. Wow. I guess. Who's the main antagonist?
What's a foil? Connor is.
Hold on, Taylor. My pen is writing.
Oh, are you stapling my guy?
No, he's doing one.
No, but I didn't staple today.
I stapled yesterday.
Kaylee's turn. I thought Gracie stapled.
I did.
Gracie did the time before, and then I did the time before that.
Okay, Taylor. There's your initial velocity, 24.6. When the ball reaches its maximum height, what's the final velocity going to be? So, you know, V is going to be 0, right? What's the acceleration of the ball? Okay, so what do you not know? Don't know time, okay? But that's not the point of the story. On this one, you're trying to find, on number 10, the maximum height. So because you don't know time, use that equation, okay? You know your initial velocity, you know your final velocity, you know your acceleration. So you're going to have D equals V squared minus V naught squared over 2A, okay? Then to get the time, here's the kicker. You're going to go from 24.6 meters per second to 0. Okay? And then to get your time, you can use V equals V naught plus AT. So use that equation and then use that first equation. Okay? All right. Going once, going twice. So. Okay, so here's what we got. We've got to work through kind of one big culminating problem. And if you can work this problem, okay, you're golden. Okay? Then, when we get done with that, then we've got an assignment with like a mini lab where you're going to try and find the acceleration, the experimental value of the acceleration due to gravity inside this room. So let's tackle this first. So here's the situation. So we're going to take an object apple, a fresh one, or whatever, and you're gonna throw it up in the air, and you're gonna time how long it takes from the point that you let go of it until it returns back to your hand, okay? That's what you've got. So from the time that you let go of it until the time that you catch it is 2.80 seconds, okay? That is the only number that you know, 2.80 seconds. From that, I want to find the initial velocity, the max height, draw a position time graph, a velocity time graph, and then I want to find the height and velocity at 1 second, and then I want to find the height and velocity at 2 seconds. And I know all of that, and I only have one number. So Eli, where can I start?
Well, you know what the acceleration is, right?
I do.
Gravity. It's negative 9.8 meters
Okay.
per second squared.
Okay, my acceleration caused by gravity is negative 9.80 meters per second squared. Okay? Now, don't do that. Okay? Now, let's talk about this. So the total flight time is 2.80 seconds. So what do you think we can assume about the time up and the time down?
They're the same.
They're the same. We can assume that this flight is symmetrical, right? So if the total is 2.80 seconds, how much time did it take going up?
1.4.
1.4. Oh, okay. So that's going to kind of be clever. So we can assume that we have 1.4 seconds going up, and then oddly enough, we have 1.4 seconds coming down. Okay? Now, let's jump down to the position time graph. So what's the position time graph going to look like roughly?
Hey, hill.
Yeah, like that.
No, wait, no, it's not.
A hill?
Wait, will it?
I don't know. I don't know.
Yeah, it's the same
My
time.
version of
You
the
reach
hill
a
is
max-
probably
Yeah,
different.
you're right, you're right.
Yeah, a
You're right.
hill.
Like a curve.
How about a parabolic curve
Yeah.
Or a hill.
or a hill?
Like an upside down U, even.
Something like this?
Yeah.
Okay?
Like, what's a Patrick's house?
Yeah. The rod in SpongeBob.
What's your gut feel? We haven't known each other that long, but what's your gut feel? I only have so many hours left on this, and I don't want to say that I said.
You're missing out.
That's I'm good.
He's a starfish and he lives under
Okay, maybe I'll retire and that's where I'll go. Huh? Never heard of it.
Really?
No.
He's the guy that really helps us on everything.
Okay. So how long did it take to reach its maximum height?
1.4
1.40 seconds, okay? And according to Topher Knizzo, 1.40 seconds, velocity is, tangent line is 0, relative maximum, however you want to put it, okay? So that's what my position time graph is going to look like. What's my velocity time graph going to look like?
A line. A negative.
Yeah.
It's going to start, it's going to start with some positive velocity that I don't know, right?
Agreed.
Yeah.
Then what's it going to do?
Slope down negatively.
Straight?
Yep.
Cool with that?
Yep.
Now, where's the ball at that point?
1.5.
1.40 seconds, but physically, where is the ball at?
Top, right?
In maximum height, top of the flight, right?
Yes, sir.
So there's you are at max height, right? Do we know the slope of the line?
Yeah.
Negative 9.
Yes. Slope of that line is meters per second squared. Now, that's all we know at this point. Okay, that's all we know. We don't know the maximum height. We don't know the displacement. A whole bunch of things we don't know. But let's just think about this. Okay? Is the initial velocity of the ball, and think very carefully before you answer this, is the initial velocity of the ball going to be equal to 9.8 meters per second, less than 9.8 meters per second, or greater than 9.8 meters per second?
The
less
initial?
than, equal to,
Greater.
greater than.
Greater.
Negative?
Wait, well, it
No,
depends.
no, no, no.
Are
This
we
is
talking
positive.
about-
This is the
1.4
initial positive
seconds,
velocity
right?
going up.
For every 1 second is
Okay?
1.8.
So is the
Yeah.
initial
What's
positive
Wow, that's really
velocity
smart
going up
thinking.
That's what we said yesterday.
Yeah.
less than 9.8, greater than 9.8, equal to 9.8?
Greater.
So how many vote less than 9.8? How about equal to 9.8? Greater than? Fantastic. Why?
Because 1.
Maggie.
Yeah.
Because it's going up, so it has to have, like, if it had a less acceleration than 9.8, then like a lower acceleration, you know what I'm saying?
No,
Then it would be small.
I'm not gonna lie.
I know what I'm talking about. Like,
And I have no doubt in my mind, okay? Now, the KU fan to your left seems very excited about giving an answer. And that's rare that KU fans are excited about giving an answer, so I want to take advantage of that. Riley?
Because the second is 1.4, it's greater than 1.
Okay,
Greater than 9.
yes. You're trying to change acceleration, which is, you're starting down a rabbit hole of pain and suffering, okay? So here's the deal. What if the ball had been thrown at exactly 9.8 meters per second? How long would it take to go to 0?
2 seconds.
Exactly 1 second.
Well, 2
So-
together.
Huh?
Nothing. They looked at me.
So since the time is greater than 1 second, I know my velocity has to be bigger than 9.8, okay? So what you'll see is that this first calculation is the most critical. If you screw up this initial velocity, everything else is going to go wrong, okay? Literally, the max and height, everything else is going to go wrong. You have to make sure that you get this initial velocity right. So here's the deal. You can go V equals V naught plus AT. At its maximum height, you know the final velocity is going to be 0. You're going to know that number. You're going to know the acceleration's negative 9.8 meters per second squared. Now, here's the million-dollar question. Do you use the total time of 2.8, or do you use 1.4?
1.4.
1.4. Why?
Because 2 point whatever will
That's
be.
how long it took to
Yeah.
reach its maximum
Yeah.
height.
Fine.
So you're going to know this number, 1.40 seconds. So I beg of you, solve this equation first. So, Wyatt, how am I going to get V naught by itself?
Subtract D times D.
No, I want to get this by itself.
I can't even see those variables.
That's an A. That's an A.
Is that -1 for V naught?
No, no, no. So V
Kind of hard
naught
to read.
plus 18.
Oh, it's
Okay, so it'd be minus 18.
There you go. Minus 18. This is going to equal V naught, right?
Yeah.
Now, this is why you solve for equations first. So you're going to have 0 minus a negative 9.8 meters per second squared times 1.40 seconds. Now, what do you know about your initial velocity? Should that be a positive or a negative number? Better be positive, because if you're going to throw something up in the air, it's not going to go very high if you throw it down. Okay? It's like, oh, it's going to go up and have a negative velocity. Cool. No, stop. So here's why you pay attention to this. Notice this is 0 minus a negative number. Oh, miracle happens. We get a positive value. Okay? So basically, so we take 9.8 times 1.4.
13.7
13.7
meters per second.
meters per second. It's cool. Now, how could you check that that number is right? How could you work backwards to see if that's right?
You could do something you could do.
Make each side's equal. Plug it back in.
Well, I could plug it back in. one option is that I find my acceleration. I take 0 minus 13.4, I divide that by 1.4, I see if I get an acceleration of negative 9.8 meters per second
You could do
squared.
displacement.
What?
Total displacement. Because you know the. No, wait, no, you don't. You don't know this. I thought we were, for some reason, you know the 25 meters question in our homework? That just like popped
That's
in my
not it.
brain.
That's not it.
Never
Okay.
mind.
Okay, now, we're gonna
That's
redraw this.
embarrassing.
So what we're saying is that we started at 13.7 meters per second. We're gonna come down like this. That's gonna be 1.4 seconds. Now, listen to me very carefully what I'm about to ask you. So this is your V0. What's the velocity of the ball when it returns back to my hand?
Negative 13.7.
This thing is symmetrical, right? So when it lands, the velocity is going to be negative 13.7 meters per second, okay? Because this thing is symmetrical. It's going to go from 13.7 to 0, then it's going to go from 0 back to negative 13.7. What is the speed of the ball when it lands? Y'all are making this difficult. Don't.
Oh, 13.7.
13.7,
Because
why?
it doesn't have direction.
Yeah, because speed is
A
a,
scalar
quantity.
quantity.
Oh,
Yeah.
okay? So it's going to launch and land with the same speed, but it will not launch and land with the same velocity. So it will launch at 13.7, but it will land at negative 13.7. It will take off with the speed of 13.7, and it will land with the speed of 13.7. So you have to be very careful about what you're talking about. Speeds, launch, land, same. Velocities, same number, opposite signs. Okay? Cool with that. Now, what else? Okay, back to the next. Now, let's talk maximum height. Could you use your velocity time graph to find your maximum height? Yes?
Yeah.
Do you know the height of the triangle?
No.
13.7
yeah.
meters per second, right? You know the base of the triangle,
Yes.
1.4 seconds. Find the area of the triangle, use 1/2 base times height. So that's one option to find your maximum height, okay? You could use 1/2 base times height, go off your velocity time graph. Could you use that equation to find your maximum height? You know your initial velocity,
Yeah.
13.7. Do you know your final velocity? Yes. Which is?
Zero.
On the way up.
Oh, yeah,
You're
zero.
going to start at 13.7, you're going to go to? Do you know your acceleration on the way up?
Yeah.
Yep. So you could also use v squared equals v naught squared plus 2ab. You could use distance equals 1/2 at squared plus v naught time. You know your initial velocity, you know your time would be 1.4 seconds. You could find it that way. All three of these are equally valid ways to find your maximum height, okay? It's a personal preference, right? It's up to you. All of them are going to generate the same answer. So what I would recommend on a problem like this, that you familiarize yourself with using all three equations. Now, so let's go back to finding the height and velocity at different times, okay? So in the name of time, here's the deal. To find the height at these times, the only way you can do that is to do 1/2 at squared plus v naught time. That is the only way that you can find a height at a specific point in time. Okay, that's the only way you can do that. You could plug in 1 second, 1.4, 2, it doesn't make any difference. So this is like a function equation. It gives you height as a function of time, okay? But what is absolutely most critical is that you use negative 9.8 meters per second squared for that acceleration, and you plug in that initial velocity of 13.7 meters per second. That's why I said if you screw up that initial velocity, everything else is going to be a train wreck. Your maximum height, your velocities, everything else, okay? So then, at 2 seconds, the only thing that changes is that you plug in 2 seconds as opposed to 1 second. So I can give you any potential value of time. Okay, so we're done with that. So here's what's going to happen on your assignment/lab. Where is?
Are you playing that? Did you start it?
I lost my
Yeah,
ball.
it is.
Okay, I got it.
No, wait, isn't he gonna do the assignment?
Oh, I did. I mean, I already did. Wait, go back. Hello?
Okay, so what the mini lab is page 3. Okay, so on the mini lab, here's the whole point: is that you are trying to find an experimental value of acceleration. If you're not sure how to do this, look at the very first lab that you all did where you pushed the cart up the ramp. Okay? When you push the cart up the ramp, you measure the total time. You worked it as a triangle, and you said, oh, so if you know how high that ball bounces, when you sketch your velocity time graph, you're going to know the area of this because you're going to know how high the ball bounced. Oh, I'm going to know the area of the triangle. You're going to know the time because you're going to know how long that took for that ball to go up. So you're going to know the base of that triangle. Find the height. That's the initial velocity of the ball. Now on the way down, what's the initial velocity of the ball? No, on the way down, what's the initial
Zero.
velocity of the ball?
0.
0. It's going to start at 0 and it's going to fall. So you're going to start at 0, then you're going to know that displacement on the way down. You're going to know that time, then you're going to find that velocity there. So listen to me. All of your labs are going to be so vastly different on this section based upon your data. So this is why on line 6, and listen to me, I say you show every step of every calculation, okay? Every step, every subtraction, everything. The only thing I can grade is your process, okay? That's it. So if numbers just magically appear, I quit grading at that point, okay? This is like a culminating lab. You want to impress me. This first question, problem number 4, you're going to throw a ball up in the air. Total flight time is 4.40 seconds. Problem number 4 is identical to the problem that I just worked. The only difference is the value of time, okay? Now, that initial velocity of the ball, if you do that right, that should be around 21, that's an ish, okay? But that initial velocity of the ball, V naught, should be around 21, because if that's wrong, everything else is going to be wrong, okay? Now, you're going to sketch a position time graph. You're going to have a whole bunch of graphs that you're going to have to draw. You're going to sketch a position time graph. I'm going to ask you, what will be the slope of the line at 0 seconds? I'm not asking, and I tell you this down below. Here's the magic code. When I say, what's the slope of a position time graph, what am I asking for?
Velocity.
An instantaneous velocity, okay? So your answer to D1, what will be the slope of the line at 0 seconds? That's whatever the initial velocity of the ball is, because that's going to be the slope of the tangent line at that point, okay? So on D, the magic decoder thing is I'm asking you for how fast is it going at that point. When you get to question number 8, okay, you have 2 spaceships, the Enterprise and Columbia. They're both moving in the same direction. One is going 450 meters per second, the other one is going 600 meters per second. So imagine here's the 2 spaceships, okay? They're at the same point at the same time. They're going to go out, they're going to stop, and then they're going to come back. And they're going to meet back here at the same time, okay? So they're both going to go out, they're both going to stop, they're both going to change direction, they're both going to be back at the same time. You're going to draw velocity time graphs for both of those ships, okay? But keep in mind they're going from a positive to 0 back to a negative velocity, okay? When you get to question number 9, you have a model rocket, okay? What's the initial velocity of your rocket going to be?
0.
0. Here's the rocket. You're going to fire the rocket, it's going to speed up. At some point then, we're going to shut off the engines, Okay, so shutting off the engines is like me throwing this thing up in the air. As soon as you shut off the engines, what's going to be the acceleration of the rocket?
Negative 9 point.
Negative 9.8 meters per second squared. Okay, I'm done. You're on your own. Get your data. Okay, get your data quickly. There's a bunch of golf balls back there.
Gotta go to the chiropractor.
Hurry.
Wow.
Yeah,
Yep.
Mason, why
They
don't
are.
we conclusions?
it is.
Hey, Pop, yeah.
That is so good.
What?
I missed the bell.
I don't think you missed them. All right, let's go to.
You want to bounce that ball as high as you get it as close to the ceiling as you can. I have a couple of people trying it. What?
Isn't the ceiling 2.5?
No, I said it's about. Oh, that's a very, very crude measurement.
Why do you have this?
Huh? All right, what? You'll see. You still got about 10 minutes, so don't procrastinate. Hey, it's Mason. What? Can't handle the golf ball, put it down.
Minus 24 meters.
Oh, hey, that's not
Yep.
Yeah. And both of his parents are gone too.
Yeah, I know.